Hello everyone, welcome back. In this session, we will learn how to compute strain energy when a beam is subjected to bending, axial force, shear force and torsion. When only body experiences work done along with deformation, then only we can say that the strain energy exists. When body experiences work done along with deformation, then only we can say that strain energy exists. Strain energy does not exist in a rigid body. There are two types of deformation. Work done happens in a body in two conditions. In first condition, when you apply the force on a body, the body elongates along the direction of the force, then only transformation, deformation exists as you can see in the figure. Now, when you apply the force on a body, for example, if I make the support as a rigid and if I try to apply the force here and also in the x direction, then the body tries to move in two different directions. This creates shear, movement and also sometimes rotation. In that case, we can observe an angular deformation. If I take along the x direction load, there is an angle deformation in this direction. If I consider a y direction load, there will be angular of deformation in this direction. Therefore, only two types of deformation happens, that is the transverse deformation or else angular deformation. In case of angular deformation, we can have movement, torsion as well as shear. In case of transverse deformation, we can experience only in case of axial force. Now let us move on to computing the strain energy due to axial force. Now consider the beam of length L as shown in this figure, and this consider a small element as indicated in this figure. This length is dx. Now I am taking the enlarged figure of this element. It is as shown here. This length is dx. Now let us apply the force F in the horizontal direction as shown in the figure. Similarly, the element also experiences a force F. Due to this application of force, there is a elongation created in the element of a length delta as indicated. So for this we can write the strain energy. Strain energy delta U is given by half into force applied F into deformation happened delta. So how this half into F into delta will come into picture? We know that due to the applied force F, there is a deformation in the element delta. There will be a energy stored in the form of triangular portion. This will be the stored strain energy. So since it is a triangular portion, we can call it as half into F into delta. Now we know that stress is equal to F by A, strain is equal to delta by L. Okay, now take equating stress and strain, considering stress and strain relation. Stress is equal to E into strain. Substituting the value of stress and strain, F by A is equal to E into delta by L. So delta will be equal to FL by AE. Now substitute this delta value in this equation 1. Equation 1 will become delta U is equal to half into F into FL by AE. Since we have considered only a small element whose length is delta x, we can replace this L to delta x. Therefore, delta U is equal to F square by 2AE into dx. This is the strain energy for the this is the strain energy stored in the small element. If we need to get the strain energy for the entire beam, we need to integrate the strain energy with respect to 0 to L. This gives us the total strain energy 0 to L square by 2 AE into dx. For example, if the beam area is changing, that is half of the length of the beam is one area and another half is another area. Let me call this area 1 and area 2. Then we can apply integration by parts method to it to compute the strain energy. That is, U will be equal to 0 to L by 2 F square by 2 AE into dx plus L by 2 to L F square by 2 AE into dx. Let the total length of the beam be L. Now let us move on to computing the strain energy due to shear force. Now in the similar manner, I have considered a beam of length L and also a small element whose enlarged figure is as shown here. Now if I apply a force in y direction and if I fixed the area of the beam, so the moment of the beam or the element will be in this pattern. The deflected shape is as shown in the figure and the deflected length is ds. So the strain energy stored in this element delta U is given by half into force Fy into displacement ds. This ds is equals to d gamma into dx. So substituting the value of ds in equation 1, delta U is equal to half into Fy into d gamma into dx. We know that shear stress is equal to G into d gamma, where G is the shear modulus and shear stress is given by force into area. Here area we need to consider this area because this area is experiencing the shear force. So substituting the values of the shear stress, F by A is equal to G into d gamma. We can calculate the value of d gamma. This will be equal to F by G A. Now substituting the value of d gamma in equation 1, du turns out to be, this is also Fy square by 2Ga. If we need the strain energy of the beam, we need to integrate the strain energy of the element. Therefore, total strain energy of the beam will be equal to 0 to L times of Fy square by 2Ga into dx. Now, let us compute the strain energy due to torsion. When we apply torque, there will be a straining or twisting in the rod. The energy stored in the rod due to twisting is called as strain energy due to torque. This strain energy can be computed using the expression delta U is equal to half into T into phi, where phi is the angle deformation. It is indicated here, that is phi. So this will be the, from torsion formula, so half into T is the torque into angular deformation. This angular deformation can be computed using torsion formula, that is T by IP is equal to G phi by dx. Phi is equal to T into dx by G into IP, where IP is polar moment of inertia. Substituting the value of phi in equation 1, we will get delta U is equal to half into T square divided by G into IP into dx. So strain energy of the beam is given by 0 to L times of T square by 2GIP into dx. Now let us compute the strain energy for the bending. As you can see that the beam is loaded with force F. Considering a small element dx, due to bending, this is the deflected shape of the beam and this is the deflected shape of the element. Due to the bending, it is creating an angle d theta at point O. Now if we try to join this two sides of the beam, it is creating an angle theta. So theta will be the angular deformation. The strain energy in the element dx can be written as du is equal to half into force into d theta. Now considering the diagram, let us compute the value of d theta. We know that, as you can see, the small element delta U, that is strain energy of the small element, can be computed as half into, here we are considering bending. The moment it is created will be created in this pattern M. This is the mzz value if we consider x and y in this direction. So delta U will be equal to half into m into d theta. From the figure, d theta can be computed. We know that dx is approximately equal to r into d theta. Therefore, d theta is equal to dx by r. And also we know that m by I is equal to E by r. 1 by r will be equal to m by E I. Substituting the value of 1 by r in this d theta expression, we will get dx by m by ei value. The strain energy stored in the element is given by delta U is equal to half, since we are considering the moment here. So the force will be moment into deformation is d theta. The moment is occurring in the element is in this pattern. This is the mzz moment. If we consider this as the x-axis and y-axis, this will be the mzz. So from the diagram we can compute the value of d theta. We know that dx is approximately equal to r into d theta. D theta can be written as 1 by r into dx. Also, we know that m by I is equal to I by m by I is equal to m by I is equal to E by r. 1 by r will be equal to m by E I. Therefore, d theta will becomes m by ei into dx. Substituting the value of d theta in this equation 1, strain energy delta U is equal to half into m by ei into dx. So we can write it as m square by 2ei into dx. This is the strain energy stored in the small element. Strain energy of the entire beam will be equal to 0 to L times of m square by 2ei into dx. These are the expressions computed for the computation of strain energy from axial force, shear force, torque and bending.